So if we put this into another problem, a rubber ball is dropped from the top of a 20-meter high building. Each time the ball bounces, it bounces back up to 80% of its previous height. Calculate to the nearest centimeter the height of the ball after the 15th bounce. When it says that Lucasito decided to solve the problem using a geometric sequence where the first term was 20, why is term fifth not the answer? Well, if T1 is equal to 20, then T15 is the height after 15 minus 1 bounces. Remember, in term 1, that's my starting height, I dropped it, it hasn't bounced at all. I can't use that as after one bounce, it was 20, which means that if I'm going to do this process, then the 15th bounce doesn't represent T15, then 15 would be the n minus 1 bounce, which means that n should actually be 16. So if I'm using his method, then I'm going to say that if T1 is equal to 20 and my R is equal to 0.8, then my n is going to actually be 16 in this case. And T16 is going to equal my starting height of 20 times my common ratio of 0.8 to the power of 15 bounces or 15 changes. This is going to give me 0.7036 meters. And because it wants its answer in centimeters, I just multiply that by 100 to get approximately 70 centimeters. Now, if Nicolette says that T15 should be the solution to the problem, then if T15 is after 15 bounces, the first term can't equal 20 because 20 is after 0 bounces. It hasn't bounced yet. So if I want to use it doing her method, then that just means that the first term would be after the first bounce has taken place, or 20 times 0.8, which means that Nicolette's first term has to be 16 for this to make sense. Then you can say that if T1 is equal to 16, R is still equal to 0.8, and now my n value is going to be 15. And I can say that term 15 is equal to 16 times 0.8 to the 15 minus 1, which would still give me the same answer, 0.7036 meters, or 70 centimeters. So there are two possible ways that I can solve this. I can say that if it's after X bounces, for Lucasito, his formula would be the height is equal to 20 times 0.8 to the power of x is just going to represent the number of bounces. For Nicolette, the height is going to equal 16 times 0.8 to the x minus 1. If it says write an equation which could be used to solve or could be solved to determine the minimum number of bounces required for the height to be less than 2 centimeters, then if I'm doing 2 centimeters, I'm going to say that 0.02 in terms of centimeters would equal 20 meters times 0.8 to the power of x using Lucasido's. And then I can use the intercept function in my calculator to figure out how many bounces this would actually take. Another way that we commonly use geometric growth is compound interest. This is a way that your savings account at the bank works. So it says Mike invests $5,000 in a guaranteed investment certificate, often referred to as a GIC. Each year, 3% interest is added to the value of the investment at the beginning of the year. Consider the geometric sequence which represents the value of the investment at the end of each year. So my growth factor, if I'm increasing by 3%, is going to be 1.03. If I want to figure out what the investment is going to be after 1 year, then I would say that I would take that 5,000, and then after a year has passed, I'm going to multiply it by 1.03 to solve for what that year is going to be worth. If I want to write a product which represents the value of the investment after 2 years, then I would say that I would take that $5,000, I'd multiply it by 1.03 to figure out what it's worth after the first year, and then 1.03 again to figure out what it's worth after the second year, or 5,000 times 1.03 to the power of 2. If I'm using the formula to write an expression which could be used to calculate the value of the investment after 10 years, then I'm going to say that I'm going to take my first term, which is 5,000, and I'm going to multiply that by 1.03 to solve what it would be after 1 year. My R value is still going to be 1.03, which means that my term value for term 10 would be the same as that 5,000 times 1.03 for my first year, and I'm going to multiply that by the common ratio of 1.03 to the power of 10 minus 1 for the other 10 changes. When I combine the 1.03 and 1.03 times 10 to the negative, 10 minus 1, term 10 is just going to be 5,000 times 1.03 to the power of 10, where remember, 10 is the number of changes that have taken place. It's not the term value, even though we've readjusted where we consider the term value to be. If it wants the value of the investment to the nearest cent after 1 year, after 2 years, or after 10 years, that's where we're going to put in the values that we had. So if I have 5,000 times 1.03, after 1 year, it's going to be worth 51.50. If I took 5,000 and I multiplied it by 1.03 to the power of 2, it's going to be 53.04 and 50 cents. And if I did 5,000 times 1.03 to the power of 10, after 10 years, it's going to be worth $6,719.58. If I want to create a formula to write an expression that could be used to calculate the value of the investment after n years, then I can say that Tn is going to be equal to 5,000 times 1.03 to the power of n. If it says, suppose an investment of P dollars earns I interest per annum, develop a formula for the A amount of the investment after n years, then I'm going to say that my R value would be 1 plus the I over 100 because it's a percentage. Term 1 is always going to be the investment multiplied by 1 plus I over 100, or multiplied by the R value once. And my A value would be the same as P times 1 plus I over 100 to the power of n years. All right, that's it. Go try some practice.